3.3 Heap sort and efficiency analysis. This is our last video of heap sort. In this one, we will complete that heap sort, and we will also do efficiency analysis. So these two things are pretty simple, straightforward. And the discussion is pretty short. After we complete preparation at this point, then just a few more steps, we will complete this topic. All right, first, so let's look at the heap sort idea. After we construct max heap here, let us assume we already have that max heap. How do we sort all the elements in this heap? So let us do a very important observation. Suppose here we have a max heap. So you know the meaning of max heap, right? The largest element is at the root, right? Max, the largest element is at the root. Okay, so now how do we make all the elements sorted in the array? Or, in other words, how do we put all the elements in place? So we use that in place terminology for the discussion. All right, so think about this. When we make elements in place, we need to do it one by one. Every time we put one element in place. Okay? The first one is the root one. Root has the largest value. How do we put that root element in place? The first question. Okay? If you can answer this question, then we are halfway there. Because the remaining, we will use the same idea again and again. So we will complete the sorting. All right, so let's look at this question first. How do we put the root element in place? So let us examine the whole array, the current array. Okay. We know we store this heap in this current array. We just imagine that heap structure in this near complete binary tree. Okay? That's the imaginary thing. Okay? First, based on the heap structure, the root element should be the first element in the array. After that, A of 0, the first one, A of 1. All right, the current, that is the current location. Okay? But we want to make it in place. What is its in place location in the array? Okay? The last element in the array. How do we do that change? So you can see a simple swap operation will do the job. Just the swap operation. Okay? All right. So if we can do the root element and the last element, we just do this swap. We put the max element in place. One swap, we put a one element in place. Okay? All right. So you can see, so simple. One step. Okay? So now let's look at the operation. The operation, we swap A of 1 and A of n. These two elements. Okay? So then A of n is in place. Okay? But you may ask, after we do this swap operation, the heap structure does not follow the max heap requirement, right? Yeah. So it violates the max heap requirement after you do that swap. But we can fix it. Yeah. That operation breaks the structure we need, but we can fix it, right? We can use the max heapify operation to fix it. Okay? Yeah, so it's fine. We can fix it. Right? All right. So we recover the heap structure by the max heapify operation. And we know that, to do that, what is the cost to do that? Fix it, max heapify, because we only fix at the root location. After the swap, the only violation occurs at the root. So you only do the max heapify from the root. Okay? Yeah. So you follow some path, max heapify, get down to a leaf node. What is the cost you need? Okay? Here I can tell you, log of n minus 1. Why n minus 1? The reason is very simple. Okay? The reason is very simple. Yeah. Because the last element already in place, so we exclude it. So we only have n minus 1 total elements in the current heap to be fixed. N minus 1 elements. Now you move down from root down to the bottom, the number of steps, log base 2 of the total elements in the binary tree. So log of n minus 1. Okay? That's the cost. We fix it. So we pay this cost. We put one element in place. Okay? After that, we put another element in place. Then we pay another cost, log of n minus 2. And so on. So we keep doing it until we place all the elements in place. Then we get a whole array sorted. So that's the idea. How about that? Okay, so you can see that's the heap sort. Excuse me. So you can see that's the whole procedure of heap sort. Yeah. Next, let me use a pseudocode to formalize that procedure. Yeah. All right. So we do iterations. Yeah. All right. First, before we do the iterations, we build a max heap, given an array. Before we do the iterations, let us build max heap first. Yeah. We know the cost. In the last video, we know the cost is big O of n. Okay? After we pay this cost, we get a max heap. Okay. All right. Next, we can do iteration from n down to 2, not 1, because the last element 1 is already in place, automatically in place. Okay. Yeah. So down to 2. Yeah. Then for each iteration, we do swap a of 1 and a of I. I start from n minus 1, every time we reduce I by 1. Okay. After that, then the current heap, because when we look at the current heap, we ignore those elements already in place. If they are in place, we do not include them in the heap. So that's why the heap size should be reduced by 1. Yeah. All right, so after that, then we apply that max heapify operation on the current array, but excluding the elements already in place. Yeah. And we fix it from starting point root location 1. Yeah. So that's the meaning. Yeah. Fix from there, that location. Okay. So after that, then we get a whole array sorted. That's the whole procedure. Yeah. So you can see, pretty short. Yeah, the sorting part pretty short. Yeah. So with this advanced data structure heap, so you can make the sorting relatively easy. Yeah. Here it's a good example showing the power of data structure, the power of the heap data structure. Yeah. All right. Then after we get a heap sort, the last step, analysis. Efficiency analysis. Yeah. How do we get n log n efficiency? Yeah. We can see it in a very fast, simple way. We can see it. Okay. All right. Here, let me use this diagram. So this is our heap. So every time when we put one element in place, how much is the cost? So we accumulate the cost of all the steps, then we get an answer. Yeah. All right. Here, so look at the first time. Yeah. After we put that in place, we need to pay log n minus 1. Yeah. Remember the previous slide, log n minus 1. Yeah. But here, because that difference is so small, so we do not bother to, separate the difference. Right? Yeah. So even we put a log of n, still we can get n log n, right? All right. So then every time you reduce the number by 1, okay, the total less than n times, right? Yeah, n minus 1 times. Yeah, but we use approximation, so we accumulate all those numbers. So we get a bigger of n log n. Okay. So you can see we get our expected efficiency growth function. N log n, that's our expected growth function. Okay, yeah. Here you may argue this way because too easy, too simple. Yeah, you may not try hard enough. So if you try very hard, use some advanced technique, probably you can get a better estimate. Yeah. So that argument is pretty good. Yeah. But I can tell you the answer, the result. Yeah. If you try that very rigorous math analysis, you get the same answer. I have that part. Okay, we use definite integral. We use integration by parts, definite integral, so we can estimate this summation. But the result, we get the same n log n. Yeah, slightly better, but in the same level. Yeah. Actually, to be more precisely, if you do that very rigorous estimate, this one, finally, we will get n log n minus n. We can improve to just that minus n. Okay, so that's improvement we can get. Okay, yeah. But the whole thing, the dominant term, still n log n. Yeah. But here to save time, so I do not go through the definite integration by parts. That the whole story, yeah. So I just skip that part. Okay, yeah. All right, so now we complete the whole heap sort. Yeah. And I want to also complete module 5. It is pretty short, yeah. But we plan to use module 4 and 5 for the final. So you just study these 2 modules for the final. Okay. Next time I will start module 6, so I will talk about some more data structure, advanced data structure. So I plan to talk about hashing, so that's one. Yeah, very useful, method, hashing. Yeah, another one, binary search trees. So, but I, basically I talk about some basic properties. Yeah, and you will have quiz number 6 for the module 6, but no questions in the final. Yeah. All right, so let's start this topic first.